Hey guys, I'm gonna try to keep it short today for you, but this lesson is kind of involved, so I don't want to rush through it just to cut the time down beneath 30 minutes. So if you're unable to watch this whole lesson at once, feel free to like break it up over 2 days, but I don't want to rush it because I want to be able to explain it well for you guys. So. Um, First of all, if you guys didn't know, I do have the answer keys for the previous day's assignment always posted on the agenda. So for today, if you look at the agenda, like the first thing on the agenda says review drawing vectors assignment. If you click that, it's a link. If you click it, it pops up the answer key. So you guys can double check your work and then see if you guys are not understanding or if you are, and if you do have any questions once you look through that, please let me know. Sometimes it's just helpful to see it done so you can kind of like, oh, I forgot a negative there, or whatever. It's just like a small mistake is often what's happening. So we talked about drawing vectors and solving them from drawing them to scale last class, and of course that has its place. So if you're trying to visually represent your vectors and include the directions in them, or if you have something that's very complicated and you don't, you can choose. You could choose to solve it algebraically, or you could choose to draw it out. So it's kind of up to you. But drawing scale diagrams for every single problem is not very efficient. And most of the time, physicists and engineers and anyone else in that kind of career field want to be efficient because you guys, your time is important. So we'll still draw vectors and directions accurately. And even with these algebraic problems, you'll still draw your vectors, but we have a better way of finding the resultant for that. So if you look at this, you know that there's a few different ways that math can help us solve vectors. So with perpendicular vectors, sorry, I'm trying not to pause this a lot, but I have like a tickle in my throat. I keep coughing. So if you have perpendicular vectors, so 90 degrees, we know we could use Pythagorean theorem and our tangent functions, our trigonomic functions to solve for the sides and angles. But they're not always going to be a perfect 90 degrees, right? So we're also going to have non-perpendicular vectors, so like an obtuse or an acute triangle. And then we're also going to have vectors where it's not even a triangle at all. You're just going to have multiple angles that you're looking at. So there are multiple ways to approach that. So if two vectors are going to be added together and they're perpendicular, so if you have a 90-degree angle, we're going to use the Pythagorean theorem and trig to solve for that. So these are pretty simple. They're pretty straightforward, as long as you remember like SOHCAHTOA and Pythagorean theorem. So remember, our resultant vector has to include a magnitude and a direction. So even though you're solving these mathematically, we still have to go back in and note that there's a unit and a direction with that. So for the first example, Neil walks 1,500 meters north and then 750 meters west from the planetarium. Find his total displacement, including his direction. So if we draw that out, he started here, because you can tell that this is, like head to tail, right? So we started here, and then we walked north, and then we went head to tail, and we walked west. So our resultant vectors is the green line. You want to solve for the resultant angle and the resultant vector, okay? Because you're trying to figure out like where are you at in reference to where you started. So we're looking at displacement on these. So displacement will always include the value and the direction. So for this, we know that Pythagorean theorem is a squared plus b squared equals c squared. And that's basically what we have here. So delta D is talking about displacement. The T subscript here is going to be talking about your like total displacement. That's what the T is for. So we're talking about the resultant vector. So that's what this is representing here. So this is kind of like your c squared, right? So you've got a squared plus b squared equals c squared. It does not matter which one you designate as a or b, as long as c is your resultant vector. So hopefully you guys know how to solve these. I would assume at this point, if you've taken all these algebra classes, Pythagorean theorem. So I'm not going to go over that real hard. If you do have questions, let me know. But basically, you're just dropping this in. So you have the total displacement squared, which represents C, part of this, equal to the one leg squared plus the other leg squared. So we're just going to solve this down and get the square root. So this ends up telling us that the total displacement for this person was 1,677.05 meters. So that doesn't give us a direction or an angle. So that's just the magnitude. So that's part of the problem. The other half of it is going to be solving for this angle. Okay, so you have to have the direction, the unit, and the angle with these. So just like we drew the vectors yesterday. So you would know like just kind of where this is falling at. It's probably going to be like about 30 degrees west of north, but we have to solve for that and know for sure. So to do that, when we have perpendicular lines or a 90-degree angle, we can use trig to solve it. So you guys hopefully are very familiar with SOHCAHTOA. So SOHCAHTOA is just helping you remember these formulas basically. So it depends on what you have here basically. So depending on which angle you're looking at, that will change how you label your sides. So for this example, we would be solving for this angle in this bottom left corner. So that would mean that directly across from it, this is the opposite side. Obviously, this is the hypotenuse. The hypotenuse is always going to be across from the 90 degrees. And then adjacent would be the other side of that. So you need to designate what these would be labeled as, because sometimes you're solving for this angle up here, or it's flipped around backwards or upside down. So you always want to designate first which sides are hypotenuse, opposite, and adjacent. Once you designate that, it's pretty simple to plop that right into one of these formulas, one of these functions, and solve for your angle. So we'll use that here. So we're trying to solve for this angle. We know that the opposite is going to be 750. The hypotenuse, we don't know. Well, actually, we do know. We just solved it. But then our adjacent line is going to be 1,500. So if we have tangent, angle here, we're going to have, so if you look here, opposite over adjacent, right? So the opposite was 750 over the adjacent is 1,500. And when you put this in here, remember to get this tangent away from this side, you're going to find like the inverse tangent. So when you put this in your calculator, when you get down to this part, you're going to solve this, and then you're going to put it in your calculator like this, your little inverse tangent line. Okay, so that's going to be whatever this is going to be x. So that's basically how you're going to solve for your angle. So the angle is what you're solving for. Make sure your calculator's in degrees, not radians. It will not work if your calculator's in radians. Hey. Okay, sorry, Dr. Lillard popped in my door. So this is how you're solving for these. So for this particular vector that we wrote out here, you're solving for this angle. We know this is the opposite, this is the adjacent. We plop that in here to our trig function using tangent, and we solve for that, okay? So you should end up with about 26.6 degrees. We are going to generally round these up because most of the time it's looking at it in sig figs. So if you looked at it in sig figs and saw that these would both have just 2 sig figs in them, so you'd round that up to 27. So if you're using all the information that we calculated, if you go back, okay, oops, ignore my writing here, but we solved before that the hypotenuse for this was 1,677.05 meters. And if we're going to round that up to have 2 sig figs, it would be 1,700 meters. And then we calculate the angle, and we're going to round this up to 27. So Neil's total displacement is going to be 1,700 meters, 27 degrees west of north. Okay, so that's where we're going to be at right here. Let me erase this before we move on. So sorry about the interruption. I do have a sign on my door. But obviously she didn't see it. So No big deal. All right, so that's how you would solve any of these that are perpendicular. So if they have a 90-degree angle, you can solve them like this. So if we're adding non-perpendicular vectors, we're going to have to use some more calculus. So if you're in calculus, you probably have gone over this stuff already, or if you've taken, I don't know what the order is, but if you've taken like pre-calc or whatever, I'm sure you guys have probably talked about these. So when you're adding non-perpendicular vectors, so if you have a wide or a narrow angle, you're going to draw the vector addition with the angles labeled and then draw your resultant. So we're always drawing the vectors out. Even though you're solving it algebraically, we're drawing our vectors. You're going to notice that your three vectors will form a triangle. And then since they're not perpendicular, we are not using Pythagorean theorem. What we need to use is the cosine rule and the sine rule. So, or cosine law and sine law. So hopefully those ring a bell. If they don't, they're not super difficult. We'll talk about them. So you might need to use some angle rules from math class, including that the sum of the angles of a triangle is 180 degrees, just to solve your final answers. And then there is the Z rule. So if you have a Z within this, it's telling you that your total angles could be 90 degrees. So I'll talk about that in this question. That makes more sense to show it to you. So example 2, Erwin carries his cat around for a walk. Erwin walks 25 meters, 15 degrees north of west, and then 110 meters, 40 degrees east of south. What is Erwin's total displacement? So if we are drawing this out, we would start out with, let me see which one was first, the 25 degrees. We would start here, draw like a light coordinate plane just to have a marker there. So you'd measure that out. So we're going to have 15 degrees south of east, and that needs to be 25 meters long. So yes, this would need to be to scale. And then once you end that vector, you're going to draw another small coordinate plane just to get your bearings. Then you would measure this one out and draw him down. Oops. Oh, I went the wrong direction. Never mind. Okay, sorry, restart. That's my bad. We're starting here. I apologize. So you'd start here and draw him. He's going up and away. So this was saying 15 degrees north of west. So if we are going 15 degrees north of west, you're going to go up and over. This would be 25 meters long. You draw another small coordinate plane. You're going to measure this one because he turned around. Okay, so he then went 110 meters, 40 degrees east of south. So we're measuring from south out 40 degrees, and he goes 110 meters. So our resultant vector here is this green line. So he went all these places, and what was his overall displacement is what we're trying to solve. So for these, this is highlighted, but it's not highlighted for any reason. You're going to use sine rule or cosine rule, kind of depending on what information you have. Sine rule works for most things. So when you guys are using the sine rule for a perpendicular, or not a non-perpendicular angle, a non-perpendicular triangle, you can use these. So this is kind of your home base right here. So you have the length of side A over sine of the angle, set equal to the length of side B over the sine of that angle, set equal to the length of side C over sine of that angle. And how this is kind of represented here is like, if this is angle A, like you designated this as angle A, the line directly across it is the length that you would use for A. So you're using like your opposites here. So the angle B is in this corner, then the length for that would be over here. So these lowercase letters are representing the lengths of the legs of that triangle, and that's what would go on top. And then the uppercase letters are representing the angles within those. So when you guys use these, you'll fill this whole thing out, and then get rid of whichever portion you don't need. So if you have, let's say we know what angle, we know what length A is, and we know its angle. We know what length B is, but we don't know B's angle, and we don't know C or the angle for C. You can cross out this part and just set these two equal for each other to solve for your missing one. Same goes for this. So if you're finding the sides, you want to use it in this form. If you want to find the angles, you can use this. Honestly, either way it would work. You're just still solving for the missing variable. Same thing for cosine rule. So for this one, you have your a squared equals b squared plus c squared minus 2bc, so 2 times b times c, which are the lengths of those sides, times cosine of angle A. You can use this as well. I have linked some websites in let me find them here. Let me see if I can switch this. Oh my goodness, I want to record this tab. Okay, so it should be on this slide now, hopefully. So I'm looking at your module for today. I have all of these websites linked on here. This is from Soft Schools. They do an excellent job of explaining how to do all of this calculus. So if you are like, I have no idea what you're talking about, use these, please. So if you click on these, they do a really, really good job of explaining how to do all this. It's really just 3 different topics. They break it down into sides versus angles. But you can figure out, like, if you're not comfortable with trig ratios, like the SOHCAHTOA stuff, you can click on these. The law of sines is here and the law of cosines is at the bottom. So that is probably helpful. Let me get back here. I want to record this tab. Is it recording? Oh, goodness. I hope so. It says it is. Okay, so hopefully this is recording and I'm not wasting all of my time. But refer back to those websites if you need to use sine rule and cosine rule. So if we're going to be adding these vectors algebraically, when you look at these, we know that a right angle would be 90 degrees, right? So if we look at these and we have 15 and 40, so if we're going back to our original problem, if you look at like this right here, this would be a 90-degree angle, right? So what we're trying to find is this angle in between. So that's what we're looking for. So if we know that this is 15 degrees and this is a Z pattern, hopefully you guys have learned about Z patterns. So if this is a Z pattern, we know that whatever angle is here should be equal to this angle right here. Okay, so if this is 15 degrees, this will be 15 degrees. So if we know we have 15 degrees coming right here and we have 40 degrees right here, we can subtract those two angles from 90 degrees to find this. So we know that that angle is going to be 35 degrees because we're going to have 90 degrees, which is what we measured from, minus 15, because we know that's equal to this 15, right? Because it's a Z pattern. So 15, so it'd be 90 minus this 15 minus this 40, which would give us 35. So we just figured out that this angle right here is going to be 45 degrees, which isn't something we need immediately because we're trying to solve for our total overall displacement and angle, but we're going to need that to put into our sine rule. So when we figured out that angle, we now have a side angle side, and we can use the cosine law. You would want to use, let me see. You can use side angle side, really, you could use it for either one. But for this, we're going to choose cosine law because we have the side. Let me show this. We have this side, we have the angle in between, and then we have this side. Okay, so the angle, like side angle side, is talking about the order in which we have these things. So we have a side, we have an angle in the middle, and then we have this side. So we're going to plop that in here to our cosine rule. Okay, so if we labeled our angles, we are going to plug it in. So if we have here, again, I know this is a lot of variables to look at, but you have the total displacement squared equals the displacement of angle 1, which we're designating as A. Okay, so here, or sorry, B. So you've got a squared equals b squared plus c squared minus 2 times b times c times cosine of angle A. Okay, so the only angle we have right now is the 35 degrees that we calculated that fit here. We don't know what this angle is. We don't know what this angle is. So we're going to have to designate this as angle A because it's the only one we have. Okay, so if we're designating this as angle A, that means that the green line has to be our length A, and then you would designate the others as B and B and then C and C. Okay, so going back to that. So this is looking at angle A and length A. So our total distance is equal to the displacement of line B plus the displacement of line C minus 2 times the displacement of line A times, the displacement of line B times the displacement of line C times the cosine of that angle. So we've got a lot happening here. So this is much easier when it's all on one screen. So this will be easier when you see it on paper. But what we end up having here is we have the displacement of our resultant line, which is what we're trying to find. So you're going to have 25 meters squared. So that was, going back here, this would be angle, or line B is what we're designating that as. So we knew that this was 25 meters, right? So we plug that in here. So you have 25 meters plus 110 meters, which these were the two legs that we knew, minus 2 times B times C again. And then we're going to have cosine times that angle. So if we have, okay, so we have this line here, and this is going to be our angle that we use because we have side angle side. So once you get all of that put into this equation, we're using the cosine rule. So we are using the angle here that we have, so we have to solve for this. The cosine A, like we have this angle of A. So that angle, we're going to line that up with the length of A, and then we have B and C as well. Okay, so when you solve these, you're going to end up with 25 meters squared plus all of these. You're going to have all of these squared and then multiplied, and then you'll have your cosine of the angle of 35 degrees. The last step of that is going to be to get the square root because this is squared. So you're going to end up with a total displacement of 90.66 meters. So when you start looking at that, we're going to find this angle using sine law. So once we figure out that the length of, let's go back. So we figured out that this length is the 90.66 meters, which makes sense, right? Because if this is 25 and that's 110 and we're comparing them, this would make sense to be about 90.6. So now we have to find your final angle using sine law. So in this case, you end up with an ambiguous case, which is probably a poor example to put on the slideshows, but this is how this was written. So what you guys will end up doing is plugging this into your sine law. So we knew that we had, let's pop back here to sine law. So you'd have length of A over sine of A equal to length of B over sine of B, and so on. So you'll plug this in and see what you have and what you still need. So for us, we're going to use the opposite here because we flipped it to find the angle. But you still have the length of the second line. So this would be of B. So you have the displacement of line B under, I guess. It's the sine of that angle. It's that equal to the total displacement, which is the leg we just solved for, and then the sine of that angle. Okay, so when we break this down, I wish this was written out a little better. Oh, I lost my tools. I can't write on this. I lost my tools when I switch back and forth. Sorry. So when we plug all this in, we basically end up with sine of our resultant angle over, well, what would this be? So this would be your 110. Yes, that's what it is. So you end up like here, up here. So you'd have your sine of your angle over D2. Okay, so that's going to be the 110 meters. And then you're going to have sine of 35 degrees over the 90.66. And then this just breaks it down. They just skipped showing that step. So we're just rearranging this to solve for the sine of the angle that we need. So we took the 110 out from this side basically and multiplied it over here. So you end up with 110 times the sine of 35 over 90.66. So when you solve for that, you end up with an angle of 44 degrees. Oops. And there's some information on that website about ambiguous angles. So if you're not familiar with this, you don't remember ambiguous angles, go check out that link and it will be very helpful in explaining that. But you basically have to subtract your angle from 180 and then add the original angle. And if it ends up being more than 180, it's not valid. So it would be an ambiguous case. So that's what we did here. So we had the angle is going to be 180 degrees minus 144, okay, which gives us 136. And then if you subtract the original angles, right, we had 15. I am so sorry. I keep getting, people keep walking in here. Okay, so I know I just got off track there. Let me restart. Where was I at? Okay. I can't like reverse it because we've already been talking for 25 minutes and it will lose everything. So let me restart for this page for you. So we had an ambiguous number for this angle, right? So if we're going back all the way back here, these angles are all labeled, right? So angle alpha is going to be this entire angle, okay? So when we figured out that that was not correct, like that was saying that this angle was 44 degrees, which obviously it's not, okay? So we're going all the way from the green line to the red line. So obviously it is not 44 degrees. So that means that that angle, we wouldn't use it basically. So you could go back in and use some other rules to solve for this. So when we come down here, let's go all the way back. We're using this angle B or beta to find the angle that you traveled from your original point to your ending point. So we're going to use the beta angle and we're going to use the alpha angle minus our original angle minus 90 degrees. So that ties back into what we did here a little bit, okay? So when we have this, we're going to have our beta angle minus our 90 degree angle and then our 15 degree angle, okay? So like hopefully you can see how these are all three related here. So we're trying to find the resultant angle basically between where we started and where we ended. So we're trying to find this angle right here. Oh, geez, I really wish is this gonna work? Can I write with that? Nope, can't write with that. Okay, can I put a pen on? Nope. Okay, so I apologize. I wish I could get my pen to come back up. So when we're looking at this, like the resultant vector, we have to be able to measure it from a coordinate plane, right? And we know that in our totality, when we were walking, we went this direction, then we went back down. So from our starting point, we know you were moving in a southeast direction, okay? We know that. So what we're trying to solve for is angle beta, and we labeled it beta because we already used A, B, and C for the cosine law. So angle alpha, we know that this angle is not going to represent the angle that we walked, right? So we're trying to measure from south, how many degrees one way or the other did we go. So angle beta is what we're trying to find. So we know that this makes a nice right angle right here, right? So we're going to use the information we have to solve this. So if we go back to that slide, okay, so angle beta is going to be equal to angle alpha, which we calculated here. So it's going to be 180 degrees minus 44. Okay, so that's going to tell us the angle alpha. So that's what we were talking about with the ambiguous case. So one way to see that is, I mean, just looking at that, you know that angle alpha, you know that this is not 44 degrees, right? So if you know that that's not correct, you subtract that from 180. and that gives you your actual angle. So if we took this and subtracted it from 180, we get 136. So that tells us that this angle angle alpha is going to be 136. And we see that that crosses over here, it kind of overlaps a little bit into this 90-degree angle that contains angle beta. So we're going to end up having angle beta is going to be angle alpha minus 15 degrees, because that's the original angle. So we go back again. Okay, so minus 15 degrees, which we know should be part of our z, it's going to be equal in there, minus 90 degrees. So you're going to have angle beta is equal to 31 degrees. So in the end, you end up with 91 meters, like your overall displacement was 91 meters, 31 degrees east of south. I promise you that most of the questions on assignments that you'll have are not this complicated. They really are not. And this is a bad example, and I wish that they had used a different example to put in here for you, because this is a lot, and I realize that. But most cases, you'll be able to just use sine law and stick your numbers in there and solve for the sides or the angles, and it is much less complicated. So on your assignment today, and I might throw in if I have time, I might put in a video of how to solve those. But for your assignment today, the ones that for solving these vectors algebraically that are non-perpendicular, the examples we're using are much more straightforward than these. So the very last thing to talk about is adding 3 or more vectors. So this would be where if you're not going to end up with a triangle at the end. So you'd have 3 or 4 or 5 different vectors, and you're going to be adding them up using components. So in this method, each vector is going to be broken down into its horizontal component and its vertical component. So your x values and your y values. Okay, so again, we're going to be using these basic trig ratios, these trig functions. These are not as complicated as what we just talked about. So I know your brain is probably exploding right now, but these are not as complicated because you're breaking it all up into x and y, which means that they're all 90-degree angles, and you can just use these trig functions to solve them. It makes it very straightforward, very simple. So each vector is going to be like your hypotenuse of a right angle triangle, and then it can be written as the sum of a horizontal and vertical vector. So basically we're going to be drawing the vector, and then basically connecting your 2 corners into a 90-degree angle to create a perpendicular set of numbers that we can use. So when we start writing these out, you'll see these variables. So you'll have the change in D1. So this is going to be your displacement of vector 1 is going to have a horizontal component and a vertical component, right? So if I draw something at an angle and then I compare its vertical and horizontal components, you're going to end up with a right angle. So this is further broken down to be shown like this. You're going to have the displacement of 1x, so this is its horizontal displacement versus its vertical displacement. And then again, this is just talking about more variables. So just be aware that this gets further broken down into x and y basically. So for this example, we're going to find the horizontal and vertical components of each of these vectors. So the first one's going to be 75 meters per second, 36 degrees east of north. I'm almost running out of time, so I'm trying to get this done before class starts. So for this example, we would draw our vector. Okay, so we're going 36 degrees east of north, and then we're going to draw its horizontal and vertical components. Okay, so we're going to break it down into its horizontal and vertical components. So what you need to do then is solve for them basically. So you're going to have your the SO part of SOHCAHTOA, right? Your sine function. So when you write these out, you're going to have your opposite over your hypotenuse. Okay, so we know that this angle is 36 degrees. We already knew that. We're trying to find out what this x component is so that we can use this later on. So we have to solve what this x side is. It's kind of opposite from what we started out doing. So since we already have the hypotenuse, we're solving for the other angles and sides. So we're going to have 36 degrees. So sine of 36 degrees is equal to your x component over your hypotenuse. So we're going to solve for this. So your vector x is going to be 44, basically just 44 meters per second north. And then you're going to solve for your y component. So, sorry, this should say east, not north, because it's going east. So we have 44.08 meters per second east. Again, then we have to solve for your y vector, so your vertical component here. So we're going to use cosine. It's going to be the adjacent over the hypotenuse. So again, the adjacent is our unknown this time. So we're going to have cosine of 36 is equal to our vertical component over the hypotenuse. So when we solve that, we're going to end up with 44.08 meters per second north. There is something wrong here. I need to fix this. This is not correct. I'm glad I caught that, but I'm sorry I didn't catch it before now. So this, obviously, this is wrong. This is a typo. I don't have my calculator handy, but this would be shorter than this line, clearly. So then, for example, B, so remember we started with having like two different directions here. So you went one direction, then you went another direction. So we're going to be adding those components at the end. So basically what we're doing is we're breaking down like what are the horizontal and vertical components of A, what are the horizontal and vertical components of B, what are they of C, of D. Like you're going to find all of the individual horizontal and vertical components for each vector. And then in the end, you will add all of those up for horizontal and vertical and determine like your overall values for your resultant vector and angle. So we did that for A. So for B, we're going to do the same thing. This time the angle comes down and over. So we have an 18-degree angle. So it's 18 degrees west of south. We know that this line is 4.3 kilometers long. Shoot, I'm almost out of time here. So we're going to end up with finding your vertical and horizontal components. So again, we're plugging these into different values that we already know, right? So if this is just flipping around your cosine function. So we use SOHCAHTOA and solve for each side. Okay, then in the end of that, you need to add them up. So you need to find your total displacement of X, so your total horizontal displacement. So no matter how many you had, you're going to add them all together. You'll find your total vertical displacement, and again, you'll add them all together. Keep in mind, if they're going opposite directions, it would be a negative. So if you initially were going like east for all of them, and then all of a sudden one of them went west, that portion of it would be negative. So you're accounting for that. So once you get the resultant vector for your total of all of your components, then you can go back and use the Pythagorean theorem to solve for your overall resultant vector. So let's see how much time we have left here. Oh, goodness. Okay. Not enough time for all of this. I'm just going to go through this very quickly, and please let me know if you do have questions. So here you have a horse in a pasture. He's basically walking around. What is his total displacement? So you're using this component vector method to solve for these. So you're finding basically his vertical and horizontal components for all of the different ways he walked. And that's why I have this kind of separated into a table. So it shows where he walked. You're finding the horizontal and vertical components just like we did in the first example. In the end, you're going to add them all up. Okay, so notice he like changed directions. So some of these are negative. So his overall horizontal displacement was negative 79 meters. His overall vertical displacement was negative 57 meters. So now you can write that, you can draw this in its own new vector using those values and solve for the resultant vector. Okay, so again, this is perpendicular because we use X and Y. So you're going to get the overall displacement is 97.64 meters. So then you want to come back in and you want to find your angles. So you would use your tangent function in this case because you have your adjacent and your opposite. So you're going to plug those values in here, find the angle, and then that is your overall displacement. Okay, so if you know that he traveled Just by looking at this graph, we know that he was traveling southwest, essentially. So you have your angle. So it's going to be 30. He traveled 98 meters, 36 degrees south of west. So I am so sorry I had to rush through that, but I have class starting here in like 2 minutes. I know the middle section of that was a little clunky. I will try to get something else up today to help explain that a little bit more. I promise that the examples you guys have will not be quite like number 2. You will use sine law and cosine law, but they're usually much less complicated than the example that was used here. So I will try to, I'll do another example that's less complicated and post that later. So please contact me if you do have any questions. And shoot, what else was I going to tell you? I had something else important to say, but I forgot what it was. So if I need to get any more information out to you guys, I'll send you a message or an announcement. So try the practice, see how it goes. You guys, I think you definitely should be able to do like the first sections and the last sections. If you're having trouble with the sine law and cosine law, please let me know. But in the meantime, it will be very, very helpful to check out those websites that I posted under the lesson on the tab, the lesson tab for the day. Please look at those and read through them. It makes a lot more sense because the examples are more simple than the one that I showed you. So check those out. Let me know if you have any questions, and we will talk about it again next time.